As we continue to refine our understanding of neural networks, it's essential to be familiar with two key components that guide the learning process: loss functions and optimizers. These elements work together to help a model learn from data and improve its performance over time. Let's start with loss functions. A loss function measures how well or poorly a model's predictions match the actual outcomes. In simple terms, it's the difference between the predictive values and the true values. The goal of a loss function is to provide a quantitative measure of how far off the model is, allowing for it to be adjusted accordingly. For example, in a classification task, the loss function might measure how close the predicted probability distribution is to the actual distribution. The smaller the loss, the better the model is performing. Mathematical and statistical measures commonly used in loss functions include the mean squared error, MSE, for regression tasks, and categorical cross-entropy loss for classification tasks. However, knowing how far off a model's predictions are is only part of the equation. We also need a way to adjust the model to improve its performance. This is where optimizers come in. An optimizer is an algorithm that adjusts the model's parameters, specifically the weights, which determine the importance of inputs, and biases, which adjust the outputs, in order to minimize the loss function. It does this by calculating the gradient of the loss function with respect to the model's parameters, and then updating those parameters to reduce the loss. This process is known as gradient descent. Different optimizers have different strategies for updating the parameters, which can affect the speed and efficiency of learning. Some of the most commonly used optimizers include stochastic gradient descent, or SGD, ADAM, which we used in the MNIST notebooks, and RMS prop. Each has its strengths and is suited to particular problem types. Loss functions and optimizers work hand in hand throughout the training process. The loss function evaluates how well the model is performing, and the optimizer uses this information to adjust the model's parameters, gradually improving its accuracy. This iterative process continues across multiple epochs, with the goal of finding the set of parameters that minimizes the loss and maximizes the performance. Understanding loss functions and optimizers is crucial to effective training of neural networks. By selecting the appropriate loss function for your task and choosing the correct optimizer, you can significantly impact the efficiency and effectiveness of your model's learning process. As we move forward, you'll gain hands-on experience with these concepts, applying them to tune your neural networks for better performance.